Okay, so let us take a step back and think about why do we care about budget sales. Remember, our objective is to model about the choice that individual or a company later on, let us say, is going to make. And the basic principle that we are going to have is that somebody, whenever they are making a choice, is basically going to choose his or her most preferred alternative from those available, right? And what we are doing in these lectures is trying to just unpack what this means. So when we say that from those available, right? This is exactly what we mean by budget set, right? Now, what we have to do is focus on these other parts, which is about choose, right? And what does it mean when we say most preferred alternative? So before we get to the choice part, let's think about what we mean by most preferred alternative and how do we actually represent these things. So what we want is basically a ranking among the different choices that this individual was making, right? And how do we represent those rankings? So there are essentially two tools that are very commonly used. So these are what are known as utility functions or indifference curves. So you can think of utility functions as basically payoff functions, which basically map uh, the choices that are available, the different consumption bundles that are available into real lines, right? And once they basically map it into numbers, then you can actually rank those numbers, right? And indifference curves are often kind of used to graphically represent preferences, but we'll see that they also have a connection with this notion of utility functions. So what is a utility function? So it is a function that represents a person's preferences, and it basically assigns a number to each commodity bundle, right? How are these numbers assigned? So the numbers are assigned in a way that the commodity bundle XY, remember we are still in this too good world, uh, that is going to get a higher number than another bundle X prime Y prime if and only if the consumer prefers this bundle XY to X prime Y prime, right? So that essentially means is that they are going to prefer X comma Y to X prime Y prime if and only if you have got that the utility from this XY is more than the utility from X prime comma Y prime, right? So this is a if and only if in the sense that this equation tells us that the consumer prefers this bundle X comma Y compared to X prime comma Y prime. And also if the consumer prefers this bundle X comma Y to X prime Y prime, then this equation also holds, right? So again, what we mean by bundles. So this can be, for example, in our world where you have got only chocolate and juice, you can think that the consumer prefers having 5 units of juice and 3 chocolates over, let us say, having 3 units of juice and 5 chocolates, right? So that can be something that is possible. And that would be a way of ranking the bundle, right? Okay. So another term that you might often hear is marginal utility. And what does marginal utility refer to? It's basically nothing but the partial derivative of the utility function with respect to a particular commodity, right? So if I have got, for example, utility as a function of X comma Y, then the marginal utility with respect to X would be the partial derivative of this with respect to the first term that you see here, right? Okay. We have said that basically the purpose of the utility function is to rank different bundles. So one option is that the consumer says that they prefer bundle 1 to bundle 2, in which case the utility from bundle 1 has to be strictly higher than the utility from bundle 2. The second option is for the consumer to say that they strictly prefer bundle 2 over bundle 1, in which case the utility from bundle 2 has to be more than the one from utility from bundle 1. But there is a third option in which the consumer says that they like bundle 1 and bundle 2 equally likely, right? So in that case, we are going to say that the consumer is going to be indifferent between the two bundles, right? If you have got that utility from bundle 1 is equal to utility from bundle 2, right? So in this notation, for example, if you have two bundles X comma Y and X prime comma Y prime, and the consumer says that they like each of these bundles equally well, then we are going to have that U of X comma Y is equal to U of X prime comma Y prime, right? Okay. If we know a consumer's utility function, then we can find the indifference curve passing through any commodity bundle, right? Why is that? Because remember, indifference curves basically answers the following question. What other bundles would the consumer find which is indifferent to the bundle that you are starting out with, right? And now we know that the link between the preference ranking versus the utility function. So this is the same as asking what are the under bundles which give the same utility as the original bundle. Okay. All right, some more terminology. So this is a bit terminology intense, but you'll see later on that there is an advantage of having this terminology. So we have defined marginal utility. Then there is another concept which is known as marginal rate of substitution. Okay, so this is often abbreviated as MRS. So what do we mean by that? That's basically the slope of the indifference curve passing through a given point. Okay. So we also can actually rewrite this expression for marginal rate of substitution in terms of the marginal utilities. And how do we do that? Well, the answer is that the slope of an indifference curve is equal to the minus of the ratio of the marginal utility of good 1 to the marginal utility of good 2. How do we get that? So remember, indifference curves would be an equation which would be of this form. So all bundles x1, x2 such that the utility from that is equal to the same constant number, right? So why is this an equation for an indifference curve? Because you are changing x1 and x2, but for in all of these cases, you are going to get that they are going to be equal to u bar, and therefore they're all going to be equal to each other, right? So this is basically tracing out all the bundles which give the same level of utility, right? Okay, now we want to find out the slope of this curve at a particular point, x1, x2, let us say. How do we do that? Well, take the differential of both sides. Okay, so what do we get on the left-hand side? So we have got that we are taking the differential of this function u, which depends on x1, x2. So you remember from your basic calculus that this is the same as the partial derivative of u with respect to x1 multiplied by dx1 plus the partial derivative of u with respect to x2 multiplied by dx2, right? And if you take the differential of the right-hand side, this is a constant. So therefore, d of constant is equal to 0. So that's how you get this expression. And now if you rearrange it, you get that dx2, dx1, which is the slope of the indifference curve, which is what we were looking at, is equal to minus of del u del x1 by del u del x2, right? Remember, del u del x1 is the marginal utility of good 1, and del u del x2 is the marginal utility of good 2, right? So let's take an example to make things a bit more concrete. So suppose that you have Rajesh, whose utility function is given by u of x1, x2 is equal to x1 multiplied by x2, right? So what does that mean? That means that suppose Rajesh is consuming 4 units of commodity 1 and 10 units of commodity 2, then Rajesh's utility from this particular bundle 4, 10 is going to be equal to 4 multiplied by 10 equal to 40, right? Does Rajesh prefer this over, let's say, bundle 6, 3, where he's consuming 6 units of commodity 1 and 3 units of commodity 2? Well, we just need to compute the utility number corresponding to u of 6, 3. So that's 18. So the answer is yes. Rajesh prefers 4, 10 over 6, 3. Okay. How do we, for example, find out the indifference curve for Rajesh that passes through the point 5, 4? Well, we need to look at all the x1, x2 such that they give the same utility as Rajesh gets from this 5, 4, right? So how much utility does Rajesh get from this bundle 5, 4? Well, we can calculate that by putting this in this utility function. So we can see that that is equal to 20. So therefore, what are the set of points x1, x2 that gives Rajesh the same utility? Well, that's going to be all the x1 and x2s such that x1 multiplied by x2 is equal to 20, right? This 20 is the utility that Rajesh was getting, right? So this actually is basically then the equivalent to x2 is equal to 20 by x1, and this is nothing but equation of a rectangular hyperbola, right? So for somebody who has a utility like this is what the difference curve equation would look like, one that passes through 5, 4. Of course, if you have a different point, let's say 7, 4, then the equation would look like x2 is equal to 28 by x1 and so on, right? Okay. How do we find out the marginal utilities? Well, remember, that's the partial derivative. So at the point x1, x2, what's the marginal utility of good 1? So we need to look at the utility function, and we have to take the derivative with respect to x1 if we want to find the marginal utility of good 1. So if we take the partial derivative of this expression with respect to x1, we see that that is equal to x2, right? And similarly, we can calculate the marginal utility of good 2. So that is equal to del u del x2 is equal to x1, right? So that's how we get it. We can also calculate the marginal rate of substitution. Remember, we have just derived above that the marginal rate of substitution is equal to the negative of del u del x1 by del u del x2. We have calculated the marginal utilities here. So we can see that the marginal rate of substitution is minus x2 by x1, right? So if suppose somebody asks you that for Rajesh at point 5, 4, what's his marginal rate of substitution. So you can actually use this expression to actually say that, okay, then the marginal rate of substitution should be minus 4, 5, right? Why 4? Because this is x2's value at 5, 4, and x1's value at 5, 4 is 5. So this is what you get, right? What is the meaning of this, right? So what it means is that at the point 5, 4, Rajesh is willing to give up a maximum of 4 by 5 units of commodity 2 in order to get one more unit of commodity 1. Now, this is a bit more trickier concept than compared to the slope of the budget line. When you were looking at the slope of the budget line, what it was telling you is that if Rajesh wants to get one more unit of, let's say, commodity 1, how many units of commodity 2 does he have to give up, right? This is determined by market prices. And so we have to look at the price, the budget line, and so on. Here, what we are asking is a slightly different question, right? Here, what we are asking is that suppose Rajesh starts out at 5, 4. He wants to have a little bit more of commodity 1. Okay. What is the maximum amount of commodity 2 that he's willing to give up in order to get that one more unit of commodity 1? Okay. One more thing to keep in mind is that if you calculate the utility at these 2 points, you might find that they are not necessarily equal, right? And the reason is because when we say that one more unit of commodity 1, this may be too large an approximation, right? So this is just meant to kind of like show you the intuition. But what the correct interpretation of the slope is that if you want to have epsilon more amount of commodity 1, basically you would want to give up 4 by 5 times epsilon amount of commodity 2 at a maximum, right? So as usual with all the derivative interpretations, when we are looking at dy dx, we often say through intuition that, if you want to increase x by 1 unit, by how much does y change? But we know that this is an approximation, right? The real interpretation, the correct interpretation is through the epsilon changes, right? So keep that in mind. So we'll often write things like this, but this is just to help you in your intuition. This is not necessarily mathematically a very precise statement, right? Okay. So let's look at one more example. So this is a different utility function for Shalu. So her utility function is given by u of x1, x2 is 4 square root of x1 plus x2. So Shalu originally consumed 36 units of commodity 1 and 14 units of commodity 2. Suppose now we reduce her consumption of commodity 1 to 25 units, but she's given enough of commodity 2 so that she is just as well off as before. So first question is, how many units of commodity 2 does she consume now? So what does that mean? That means that originally she had this bundle 36, 14, right? Now her bundle is 25, some unknown amount. Let's call that y. The link between the two bundles is that it gives her the same amount of utility. Okay, that because we know that she's just as well off as she was before. So we have to solve for this y. How do we do that? Well, first let's find out what's the amount of utility that she had from before. So if we put in x1 equal to 36, x2 equal to 14 in this equation, we will end up getting 4 of square root of 36. So that's 4 into 6, 24, plus x2 equal to 14. So therefore we have 38. So that was the utility level before. Now x1 is equal to 25. We need to find out the value of x2 such that the utility is equal to 38, right? So this is basically this equation that you see here. So this first part is basically 20, and so therefore y is equal to 18, right? So we see that as compared to before, she is consuming more units of commodity 2, and this kind of makes sense, right? Why? Because her amount of consumption of commodity 1 has gone down, right? So she needs somehow to be compensated so that she is just as well as before, right? So that's why her consumption of commodity 2 has gone up. Okay. What's the marginal rate of substitution when she's consuming a bundle x1, x2? So again, we can use our old formula, which is that the marginal rate of substitution is equal to the negative of the ratio of the marginal utilities. So in the denominator, we have del u del x1, which is marginal utility with respect to x1. So here, if we go and put that equation, so we have got we have to take the partial derivative of this with respect to x1. So we have got 4 into half, right? So that is 2. And this x1 comes in the denominator. And the marginal utility of x2 is going to be just 1, right? Because we have got plus x2 here. And so therefore, you end up that the MRS is given by this expression that you see here. Okay, so I hope now that this is allowed you to become more comfortable with these different notions. Okay, so now we put these different things together and we start talking about choice, right? Remember, choose his or her most preferred alternative from those available. So we have discussed what does it mean by those available. That's the budget set. We have discussed by what does it mean about preferred alternatives. So those are the utility functions or indifference curves. Now we are going to focus on this choose, right? And this is basically the commodity bundle that's going to be chosen by a utility maximizing consumer from a given budget. So what's the general problem? So this is the general problem. So you want to max your utility by choosing the amount of commodity one and commodity two that you're consuming, and you are constrained by the budget constraint. Okay. Now we are going to discuss a particular solution here. We are going to assume that the utility function has several nice properties, right? So that it is well behaved. We are not going to go into details into what well behaved means, but basically all of that will lead to nice solutions to come out. And we are going to assume that the problem has an interior solution where you have got that this at the end the solution would involve choosing both positive amounts of both the goods, right? Okay. So this is something that if you want to unpack what does the word well behaved mean and what happens when you have got, let's say, solutions on the boundaries and so on. Again, you should be taking a course in microeconomics. We are going to abstract away from all those things because we are going to assume that all these properties are going to be satisfied in whatever problems we are discussing in this course, right? So let's focus on how the solution works. So we can solve this using the Lagrangian method, right? So if this is something that is familiar to you from, again, basic mathematics, these are basically techniques which are useful when solving problems involving optimization under constraints, right? So the procedure is you write down first the Lagrangian, right? What is the Lagrangian? So that is the objective function that you are trying to maximize plus lambda, which is known as the Lagrangian constraint, multiplied by m minus p1x1 minus p2x2. So if you notice, we have assumed that this holds with equality. And the reason we are able to assume that is that we essentially, one of the nice things when we say that utility function is well behaved, it means that the utility is increasing in both x1 and x2, right? So that means that we will want to exhaust our income that we have. We are not going to leave money around. So therefore, p1 x1 plus p2 x2 less than equal to 1, less than equal to m. This is going to hold with equality, right? So p1 x1 plus p2 x2 equal to m. And so therefore, we can write this in this way. So this is actually at the optimal point equal to 0, right? But this is how we incorporate the constraint. Okay. So what are the first order conditions? So that is going to be given by three equations. So we are going to have the partial derivative of L, which is this Lagrangian, with respect to x1 is going to be equal to 0. We have partial derivative of L with respect to x2 is going to be equal to 0. And we have the partial derivative of L with respect to this lambda is equal to 0. So three equations, and we are going to use that to derive three unknowns, right? So x1, x2, and this lambda. Okay, so what happens when you take the derivative of this L with respect to x1? So from here, we have got del u del x1, right? And from here, we have got minus lambda times p1, and that we are going to set equal to 0, right? So you end up getting that del u del x1 is equal to p1. The second equation similarly gives you del u del x2 equal to p2. And the last equation, del L del lambda equal to 0, gives you m minus p1 x1 minus p2 x2 equal to 0. And so therefore, p1 x1 plus p2 x2 equal to m. So this is notice that this is the same as this constraint that you have. And we have argued before why we are replacing this less than equal to with this equality. Okay, so the first two equations actually give you, if you divide equation 1 by equation 2, you end up getting that del u del x1 by del u del x2. So therefore, the ratio of the marginal utilities is equal to p1 by p2, which is the ratio of the prices, right? And if you multiply both sides by negative 1, you end up that minus of del u del x1 by del u del x2, which is nothing but, remember, the marginal rate of substitution, which we derived earlier, right? So this is exactly what we had derived earlier. So you end up getting that the marginal rate of substitution is equal to minus p1 by p2, and this is, if you remember, nothing but the slope of the budget line, right? So this is the tangency condition, and essentially from these equations you can solve for the optimal value of x1 and x2, and that essentially solves the problem for you. Okay, so let's look at a couple of examples just to fix our ideas. So suppose that you have got Rajesh, whose utility function is, as we had discussed before, imagine price of good 1 is 1, price of good 2 is 5, and his income is 300 units, right? We want to here solve for the optimal consumption bundle, which is going to be X1 and X2. So one way to do it is that, again, you set it up as a Lagrangian and solve for the optimal point. But you can also use the results that we have. We know that this is what characterizes the first order conditions. So this equation and this equation, and we can directly go there as well, right? So these are the two equations that we had before. And if you now plug it in, remember del u del x1 for this utility function is going to be x2, and del u del x2 for this utility function is going to be x1. So this first equation just becomes x2 by x1 is equal to P1 by P2, and you are given the value of P1 is 1 and the value of P2 is equal to 5. So therefore you get that x2 by x1 is equal to 1 by 5. And from the second equation, if you plug in the value of P1, P2 and M, you end up getting that x1 plus 5x2 equal to 300. So you can solve these and you end up getting that x1 is equal to 150 and x2 equal to 30, right? So the optimal choice that Rajesh is going to make, if he had this utility function and these were the details about the prices of the goods and the income, is that he would choose 150 units of commodity 1 and 30 units of commodity 2 to consume. Okay, we can also look at what Shalu would do. So imagine this was Shalu's utility function as we had discussed. And suppose price of commodity 1 is 1, price of commodity 2 is 2, and Shalu's income is 24 units. What would Shalu's optimal consumption bundle be? Again, we use the first order conditions from before. Del u del x1 by del u del x2 is equal to P1 by P2. And this is the second one, the budget constraint. So if we take the derivative with respect to x1, we get that this is 2 by square root of x1. The derivative with respect to x2 is just 1. So this is what the left hand becomes. And P1 is equal to 1 and P2 is equal to 2. And so therefore you end up that this is half, right? And similarly, we get the budget constraint from this information that is here. And so therefore, if we solve these things, we see that that becomes x1 is equal to 16 and x2 is equal to 4. That's how we can solve it. So we can also actually apply the same thing to, for example, think about more complicated settings. So for instance, recall that we studied intertemporal budget constraints, but we could have also solved for intertemporal choice there, right? So this is one example. Again, imagine that Rajesh is the one choosing, but now rather than choosing between two different commodities, he's choosing between consumption in period 1 versus consumption in period 2. So think about he's choosing between consuming when young versus consuming when old, or consuming today versus consuming next year, and so on. His utility function is given by u of C1 is equal to C2, where Ci refers to Rajesh's consumption in period I, right? So C1 is Rajesh's, how much does Rajesh choose to consume in period 1, and C2 is how much does he choose to consume in period 2, right? So these are the preferences. So, and we also need the budget constraints. So we are also given some additional information, right? So there is no inflation, interest rate is 10%, and Rajesh has income 100 units in period 1 and 121 units in period 2. And we are asked to solve for the optimal choice of consumption in 2 periods. Well, how do we do it? Well, remember, the problem is we need to maximize this utility function, right? Subject to the budget constraint, right? So what we need to do is you need to use this information to figure out the budget constraint. And this is something that you have already done in week 2, right? Remember our discussion of intertemporal budget constraint. So if you go back and recall, the intertemporal budget constraint is something that look like this. So the present value of consumption is equal to the present value of income, right? And here we are told that R is 10%, M1 is 100, and M2 is equal to 121. So if you plug those all in, we get that the intertemporal budget constraint is something that is going to look like this expression, right? So C1 plus C2 by 1.1 is equal to 100 plus 121 by 1.1. So if you do the simplification, the right-hand side becomes 210. And Rajesh is basically choosing C1 and C2 to maximize this utility function subject to this budget constraint, right? So this is very similar to the example that we had before, right? The only difference is there we had P1 x1 plus P2 x2 is equal to M. But here, basically, you have P1 equal to 1 and P2 is equal to 1.1. So again, you should go back and think about the interpretation of the slope of the intertemporal budget constraint here. I'll let you do that as an exercise. But let's just look at how to solve this problem. Now, mechanically, this is as exactly the same as before, right? So you again have the first order conditions, which are these, and you can just basically plug in, right? So you want to kind of like do
del U del C1. So that's the C2, del U del C2, that's the C1. You have got P1 by P2. So therefore that becomes your 1 divided by 1 by 1.1. So that's 1.1. And you have got the budget constraint, which is this expression that you see here. And now if you solve for this, again, two equations in two unknowns, you can see this, that this is going to be C1 comma C2 is going to take the value 105 comma 115.50, right? So that's again something that you can see that that's the beauty of this methods, right? That if you once you understand how this works, you can kind of apply it to different contexts, right? So we started off by looking at something very abstract. We saw that the same principle can now be applied to intertemporal choice problems, right? And in fact, we'll see later on that the same idea actually generalizes to thinking about choice under uncertainty as well. So the main reference that we used for our discussion here is the textbook by Halvarian that we have mentioned before as well. And if you want more details, this is one place to look at. And of course, these are some things that are again dealt again in much more details if you take a course on microeconomics. So that is a place to look at if you want to kind of focus more on these details. But for us, we'll now want to move on to use this as a foundation to thinking about decision making under uncertainty.